podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to do something completely different. And we're going to talk about Einstein's theory of gravity.
So I heard a joke one time that Einstein's not that smart. He got the I before E wrong twice in his name.
Yeah, wow. He was not the best student. I think everyone
Dropped out of school to become a patent clerk, didn't he?
Yeah, everyone heard the story, like that he couldn't do third grade math. Okay, that's comical at best. But he did not finish his college career initially. He experienced some discrimination because of his religious faith in the country that he lived in, and so he just quit school and started thinking about things on his own.
He actually left.
He left, I believe, Bonn.
Because of the Nazis, right?
Right, and this was in the late 1800s, well before World War II, and the Nazi regime. And he went to Switzerland and became a patent clerk, where he could work freely and he wasn't discriminated against. And then only after did he come up with these 4 brilliant ideas was he accepted back by the German people, even though he was still a Jewish man. But it wasn't Einstein that started thinking about gravity, was it?
No.
Now, who was that guy? Who thought of gravity?
Isaac Newton.
Yeah. And so for many years, people were happy with Newton's work on gravity. And really, the idea of gravity was synonymous with Newton's name, because he was the conqueror of figuring out the moon and the earth and the stars and the sun and all of those other items. And Newton had 2 things to say about mass and weight and gravity. I'm sorry, he had 3 things. The first thing he had to say is, hey, look at my second law. The sum of the forces is equal to mass times acceleration. And if an object is falling, and assuming that there's no air friction on it or no air resistance, the only force acting on it would in fact be its weight.
So that's why different items with different weight actually fall at the same speed.
Fall at the same rate. That it's just the acceleration due to gravity is just a ratio of mass to weight.
I think when we talked about projectiles, we said gravity doesn't care.
Yeah, gravity is dumb. That was sort of my tagline this year. And so when the mass cancels, because it's identical, what you see is that the acceleration due to gravity is in fact a negative value, and it turns out to be negative 9.81 meters per second squared. And out of this leads 2 really interesting facts. The first is that the mass helps determine the weight. It plays a very important role. Massless objects don't have weight. Maybe that goes without being said, but massless things cannot have a weight because of our weight equation.
Right.
Okay? Very important role.
And therefore, the more mass on the Earth's surface, the more weight.
The more weight, absolutely. So a huge role in describing weight, which was a difficult concept in the 1700s. And then mass also determines inertia.
It's easier to push a golf ball than it is a bowling ball.
Right, where, if we remember right, inertia, the tendency of an object to do what it's doing, right? Well, these are 2 very different things. Yeah, it makes sense that heavier objects are harder to push, right? But they're not the same idea. Inertia is different than weight. They're connected through this concept of mass. And people, for hundreds of years, took this idea for granted, that the 2 were very convenient facts of the second law, but they were in fact disconnected, that they did not have to be connected, until Einstein came along. And once again, Einstein was a genius, so he asked some really hard questions. So on page 416 of your book, we're going to follow along, and we're going to do the plus for you. So once again, you're welcome, in case you forget to say thank you. So here we go. It says the following exercise will provide some insight into Einstein's theory of gravity, the general theory of relativity. Rewrite the equations on the previous page using subscripts to distinguish between inertial mass and gravitational mass. Okay, so what we would say here is that the sum of the forces is equal to mass times acceleration. And if an object is just falling, this is due to its weight. Okay. And the weight force would be equal to the gravity weight, gravitational, times the acceleration due to gravity. And this inertial, or this net force, is due to the mass's property of inertia. So we would write m inertia times the acceleration. So we rewrote those equations, even though we know that both of these m values represent the exact same thing. Step 1 done.
Next question says, below is a diagram of two balls of different masses being dropped. The student is at rest on the earth and drops the massive red ball and the less massive blue ball at the same time from the same height.
Okay, so massive red ball, less massive blue ball. Okay, and what does it go on to say? It shows us this picture, and in the picture it shows us, of course,
The balls hit at the same
the
time.
balls are going to hit the ground at the same time.
Because gravity doesn't care.
It's dumb.
So then it says, how does the student describe the motion of the ball?
Okay.
So I drop it out of my hand, it's speeding up, it is accelerating toward Earth. They both go at the same speed.
Okay. What else might they include? So that it sees them both getting faster, but what key word are we forgetting to use here? That they're accelerating due to
Gravity.
And does gravity have a specific rate?
Of course.
And so I actually accidentally asked question B. What value will the student get for her measurement of the acceleration of the ball?
And that's 9.81 meters per second squared.
So what you'd see here is that you would see that this g is related to the acceleration, all right, because this is just a special kind of acceleration,
Right.
and negative 9.81 meters per second squared. So whether you wanted to talk about the gravitational properties of mass or the inertial properties of mass, they both accelerate due to gravity. Okay?
Correct.
Hands down. So that gives us some insight into Einstein's thought process. Number 3 then says,
The diagram below, the procedure is repeated, only this time a rocket ship is accelerating, not constant speed, but speeding up, accelerating at 9.8 meters per second every second. The rocket ship is in deep space and there is no net gravitational force acting on it.
okay,
So now we're going to ask some questions.
so you see the picture up on your screen, and or in your book on page 416. What does the astronaut in the rocket ship see? So first of all, his frame of reference happens to be
The rocket ship.
the rocket ship. There are no windows. He's not by anything. He can't see anything or feel any gravity from anything. He's just on the rocket ship.
Correct.
So if he were to let go of the balls, the same balls he used in the first experiment, what would he notice about the balls?
The balls would fall toward the bottom of the rocket ship, accelerating, okay, and hit at the same time.
So the same result.
The same result.
So in the first experiment with the woman dropping the ball, she's at rest.
Right.
She's on Earth.
Correct.
Okay, and in the second experiment, the astronaut is not at rest.
Correct.
He's getting faster.
There's no gravity,
He's accelerating.
and he is accelerating. Correct.
So do they both make the same observation?
Absolutely.
Yeah, and that's really strange because we have what we would call an at-rest reference frame, and we have an accelerated reference frame, and we're getting the same exact result. The astronaut would see the balls falling.
Correct.
Correct. He would see them falling
Toward the floor,
toward the floor at a rate of.
9.8 meters per second.
So the rocket ship, because of its propulsion force, is simulating Earth's gravity.
Correct.
Wow. So how would the astronaut explain this? He knows there's no gravity, and if you're an astronaut, by the way, you've probably taken a physics class or 10.
Right.
Okay? What would he say? He knows he's not at rest. He knows he's not on Earth. So in order to simulate Earth, what would he have to see? What would he have to say?
He would say that the balls are really at rest, and it's the rocket ship that is accelerating up to them.
So he's in an accelerated reference frame.
Correct.
And it's just like Earth.
Right.
what would the astronaut measure for the acceleration of the massive red ball and the less massive blue? Well, because mass doesn't matter,
Right.
the force is going to act the same on both objects. You go back to our gravity is dumb statement. He's going to measure 9.81
Correct.
meters per second squared. Okay, that's really strange. Question 4 gets kind of tricky. Question 4 says, you have the ability to see the rocket is accelerating up. Okay, how do you explain the ball's positions after each 0.2 seconds?
Oh, so I'm standing off to the side, looking in, and I can see it. Okay, so what I see is the balls are not moving and the rocket is.
Okay, so
Because there's no force acting on the balls themselves. The balls stay there and the rocket accelerates to hit them.
so you would see the balls floating.
Right,
You wouldn't see them moving.
correct.
All right, so we have our glass rocket ship, and we would see it accelerating due to a net force on it.
Correct.
And from the perspective of the ball, though, maybe I'm jumping ahead. I don't think I am.
From the perspective of the ball, well, are you saying if the ball was looking at me or if the ball's looking at the rocket
If the
ship?
ball's looking at the rocket ship, it would see, hey, the rocket ship is moving at me
Right.
at 9.8 meters per second squared. The rocket ship to the ball would say, hey, the ball is falling towards me
Correct.
at 9.81 meters per second squared. So the concept of it's all relative actually comes right out of Einstein's theory of relativity. It's about
Correct.
perspective and from what point of view are you measuring from. And so because the rocket's position is changing every 0.2 seconds, that would help explain this. It's an accelerated reference frame. And I suppose we're going to leave you guys with number 5. Can you think of an experiment that the student in the room or the astronaut in the rocket could perform to determine if gravity is pulling the ball down or if the rocket is accelerating up? So, by the way, you kind of did this already with our elevator talk in the previous podcast. So, signing off, this is Mr. White.
And Mr. Sadler.